And therefore, for all guys who listen to this podcast, be happy if you get a paper rejected. It can turn out very successful for you. Don't be frustrated. That's normal.
Welcome to episode 76 of the Engineered Mind podcast. I'm your host Joseph, and on this podcast I'm talking to researchers, scientists and engineers and how their work is shaping the world around us. For this episode, I am very honored to welcome Sepp Hochreiter to my show. Sepp is heading the Institute for Machine Learning, the LIT-AI Lab, and the AUDI.JKU Deep Learning Center at the Johannes Kepler University of Linz in Austria, and is director of the Institute of Advanced Research in Artificial Intelligence. His contributions to the long short-term memory, short LSTM, and the analysis of the vanishing gradient are viewed as milestones and key moments of the history of both machine learning and deep learning. Sepp laid the foundations for deep learning in two ways. Dr. Hochreiter's seminal work on the vanishing gradient and the long short-term memory were the starting points for what became later known as deep learning. LSTMs have been overwhelmingly successful in handwriting recognition, generation of writings, language modeling and identification, automatic language translation, speech recognition, analysis of audio data, as well as analysis, annotation, and description of video data. In this podcast, Sepp and I talk about Sepp's early days, his interest in mathematics and career, how to become an AI expert, his phenomenal work on LSTMs. We talk about his collaboration with his former thesis supervisor Jürgen Schmidhuber. We talk about the infamous vanishing gradient problem, and much more. And now, ladies and gentlemen, here's my podcast with Sepp Hochreiter. Sepp, welcome to my show. It's really an honor to have an expert like you on my show. So thank you so much for being on the Engineered Mind podcast. What we want to get started with, Sepp, is can you give the audience maybe a quick bio of who is Sepp Hochreiter and what do you actually work on?
It's also an honor for me to be on your podcast, and yes, I hope to enjoy it, and I hope the listeners enjoy our conversation. I'm best known perhaps for LSTM, which stands for long short-term memory, and also for a thing which is called the vanishing gradient. If you have deep neural networks or recurrent neural networks, the gradient gets scaled down or explodes if it gets propagated back. But LSTM is probably everybody associates with my name. I'm in Linz, heading here in Linz, the Institute for Machine Learning, heading here is a LIT-AI Lab, Artificial Intelligence Lab, and I also I'm one of the directors of the Institute for Advanced Research in Artificial Intelligence, which is a private-funded research institute. Yes.
Very interesting. Very busy man. Sepp, so what we want to get started with, let's get back in time and maybe you can explain to the audience how you got interested in computer science and mathematics. Because I listened to a German interview from you where you said how enthusiastic you got about mathematics, and maybe you can explain how you got interested in these topics.
That's really very early. Almost nobody asked me going back so far. Yes, it's true. I grew up at a farm, and where you wouldn't go to the college or something like that. But at some point I got first interested in chess. It's a game chess, and I had some friends, and they're also playing chess, and we always played chess in the library. But these friends also were very enthusiastic about physics and mathematics. And we played chess in the library, but we also read math books, we read physics books, and did all this kind of stuff. And but for my career, I only took not the way directly to the college, but it was a secondary education system. And I always was fascinated with this math and stuff like this. But my problem was because I didn't do the college, I could not study math. Then I looked up what can I study, which has a practical side, because I only was allowed to study some practical things. And this was computer science. Computer science is closest to thing. I didn't study computer science because I'm with computers. of course, I had a Commodore, stuff like this, but it was very close to math. And there I started first at the Fachhochschule, University of Applied Sciences, and then I changed from the University of Applied Sciences to the Technical University in Munich. And as I was in Munich, the computer science study was then a little bit boring because, as you know, I was interested in math, but I already had all the math classes read in the library. I already know everything. And then I focused on computer science, but it was also very obvious for me and easy for me. And since computer science study was boring, then I also studied mathematics. It's a Fernuni Hagen, which is a distance learning study for math, but it was boring until I met one guy. The guy is Jürgen Schmidhuber. He gave a lecture on neural networks. And I said, wow, it's the first thing which is interesting because all other stuff I learned was 20 years known. In math, it's 100 years known. But with these neural networks, you can try out new things. You can try out new architectures and play around and can have your own discoveries. This was the first interesting stuff where I got interested in this topic because all other topics were maxed out. There was nothing to explore anymore. And this was then where I started all this thing concerning neural networks.
Very interesting. We'll talk about Jürgen in a couple of seconds. So your diploma thesis in 1991 was called Untersuchungen zu dynamischen neuronalen Netzen, which would be translated into investigation for dynamical neural networks, where you basically had like a lot of sophisticated derivations, like working with Jacobians and things like that. I had a look at your diploma thesis, very sophisticated mathematics, very interesting to read. And if anyone who listens to the podcast wants to have a look at the English version of it, there's also a publication from Sepp Hochreiter, Joshua Bengio, Paolo Frasconi, and Jürgen Schmidhuber called Gradient Flow in Recurrent Nets, the Difficulty of Learning Long-Term Dependencies. Also very interesting read. I had a look at it before the podcast. When we talk about LSTMs, maybe let's start from the ground up. Maybe we start with recurrent neural networks, Sepp. Can you explain what are recurrent neural networks and what's the problem or the disadvantages of recurrent neural nets before we then jump to your infamous LSTMs?
Yes, as with Jürgen, I very early came in contact with recurrent neural networks before for my diploma thesis working on LSTM. I did a practical work also with Jürgen, and it was about reinforcement learning, actor critic. Here, Jürgen's idea was, hey, this actor critic should be recurrent neural networks. What's the difference between feed-forward neural networks or fully connected neural networks and recurrent neural networks? Recurrent neural networks have a feedback connection, a feedback loop. And this allows you to store information over time. For example, if you have a neuron, so a neuron can activate itself if it's activated and therefore memorizes that it was once activated. And therefore, these recurrent neural networks can store information over time. So much more powerful than this feed-forward or fully connected neural networks. Even recurrent neural network have Turing power, so Turing complete, meaning recurrent neural networks can do everything what you can do on a computer. Your computer, your Microsoft or Unix operating system can be simulated or emulated by recurrent neural network. So very powerful. Jürgen there said, hey, let's do reinforcement learning with these very powerful neural networks, this recurrent neural networks, which can memorize what happened in the past. That was as I started. But then we figured out, but also the community figured out, they have a big problem. The big problem is they should memorize some things, but they don't do. They don't learn to memorize something. They only focus on, if you have a sequence, if you scan a sequence, they only focus on the last element of the sequence. And that's a problem because if you have something like a man in black trousers crosses the street, or if I say the street is crossed by someone in a black trousers, which is a man. Mm-hmm. Once I started with man, and in the other sentence, the man was the last word. But I want to express the same thing, meaning in language, every word might be important. It could be at the beginning, it could be at the end. And also for what I did later is protein sequences, DNA sequences. Everywhere in the sequence, there could be something very important. Therefore, you should not focus on the last thing. You also should memorize which is far apart because it could be of interest. And recurrent neural networks couldn't do that at this time. So I forgot it. If you scaled it up, then your network exploded. The gradients become so large that the weights became very large values, and the network could not be run anymore. Therefore, there was a problem. In theory, recurrent neural networks can store something, but in practice, they didn't do it.
Mm-hmm. So then there's a big problem with recurrent networks, which you already alluded to. So can you explain why they don't work? There's this thing called vanishing gradient problem. What I would like from you is maybe you can explain to the audience, what is this vanishing gradient problem? And while you were writing your diploma thesis, was it like a eureka moment where I said, hey, this is it, I found it? Or was it like a step-by-step that you found basically, or moved forward in step-by-step smaller steps?
Yes, I can tell you. The problem by recurrent neural network at this time couldn't store any information was they could not learn to store it. And for learning to store it, we did it with gradient descent, implemented as backpropagation. It's also still very popular. And they couldn't learn it. Why couldn't they learn it? Because there was no information. How do you transport the information that they need something to store from the target where you need the information to where the information is presented to the neural network by propagating the delta errors back, by propagating it back. And if the error says, hey, I need this piece of information, then I learn to adjust the synaptic weights of the neural network in such a way that this information is entering the neural network and kept. But the problem was this gradient was vanishing. I propagate back the delta errors, but with every propagation step, they were scaled down. And if I were scaled down by 0.9, if I go 100 time steps back, it's 0.9 to the power of 100. And now it's a very small number. Now nothing is there. And now there's a misunderstanding. Some say, yes, why shouldn't this be a problem? You only should scale up the learning rate. Then you can compensate for this vanishing gradient. That's true. But there's one problem. The bigger problem is with the vanishing gradient is that for some samples, it's perhaps 10 to the minus 10. For other samples, it's 10 to the minus 6. Mm-hmm. And the bigger problem is that between samples, there's such a big difference, and therefore you cannot adjust the learning rate. If you adjust the learning rate to the 10 to the minus 6 and you scale it up so that you can learn it, you still lose the 10 to the minus 10 guy. If you scale it for the 10 to the minus 10 guy, then the 10 to the minus 6 is much too large and the weights explode. You cannot do this. The problem with the vanishing gradient is not that it's vanishing because I can scale it down. No, the problem is different samples have very different, how should I say, scales of propagated by deltas. Another problem would be if information enters the network between, because then a new information is overlaying, is superimposed with old information and it gets overwritten. But if there's no noise, there's no thing, the discrepancy between samples as a gradient gets propagated back makes learning impossible.
Mm-hmm. I see. So the English paper that I mentioned previously, if people want to have a look at the summary of your diploma thesis, it also mentions that there are things called backpropagation through time, which is BPTT, which you just mentioned, and then real-time recurrent learning. And there's two things that you mentioned in this paper, one being the blow-up, and then the second, which we already discussed, is the vanishing gradient. Could you maybe understand or explain how can we understand it mathematically? You kind of explained it a bit, but what is this blow-up thing? what happens with the machine?
So the thing is, if you propagate a piece of information like a delta error back, either on average is below 1, then it's this, what I already mentioned, vanishing gradient, it's scaled down. But perhaps if you propagate it back, it's larger than 1. Then the delta error is increased at every time step by a factor larger than 1, and it's growing, it's exploding. But then what you have, you only focus at the beginning of the sequence, and small differences in the beginning of the sequence blow up and completely dominate your network. But even more serious, it's learning does not work because the numbers are too large. The weights get 1 million, a value of 1 million or whatever, which doesn't make sense anymore. Therefore, this exploding gradients, it's the delta errors increase to big numbers and make learning unstable.
I see. Very interesting. Thank you so much for explaining that, Sepp. Going back to your diploma thesis working with Jürgen Schmidhuber, could you explain, I asked it in the previous question, how was it for you writing the diploma thesis? How often did you meet with Jürgen? How was it working with him? How much input did he give to you? And again, like, was it like a one big eureka moment where you sat in front of your thesis and said, this is it, while deriving a lot of equations, which you can see in your diploma thesis? Or was it like gradual improvements of your idea?
I can tell you this, that I got these questions sometimes, especially from my students. First of all, it was a very interesting time as I wrote my diploma thesis. Jürgen was on the leave for his postdoc stay in the States. Therefore, at this time, I didn't meet him too often, but he gave me a very specific task, and I should do in my diploma thesis the chunker system. The chunker system, I now Jürgen at some of his blogs explain it again. It's a very smart thing. If you can predict a sequence, you can compress a sequence. And if your original sequence contains more of subsequences which are deterministic, like it's always A, B, C, D, you only have to store A because you know it's B, C, D always comes. And that's a way of reducing the size of the sequence and trying to get rid of the vanishing gradient, because if you have reduced the sequence, you have a shorter sequence. If you have a shorter sequence, vanishing gradient is not so problematic because you don't have to propagate so many time steps. That was my goal. It was a great idea, but what happened then is what I said, hey, why can this recurrent neural network not learn it? And I was always curious, okay, Jürgen has a solution. It's very smart, cool idea, yeah? But Jürgen brought me also to this problem. I said, hey, I, as Sepp, can construct a neural network which can do it. But I can this learning algorithm not figure it out. And now what I did do is that I know exactly, I have to adjust this incoming weight. If I make it larger, it will store there was a 1 in the input sequence. Why can it not see it? And now what I did a lot of printfs. That's how I looked at it. I want to see what's happening every step. My whole screen was full of numbers. Every time step, what's going here, what gradient information I have here. And doing this printouts, going really down to the details, I saw, of course, there's a number 10 to the minus 10. Therefore, adjusting the weights. Even if the weight is adjusted, it has no effect. I wouldn't see it. Now I see it. And it's going down to the details and printing out for every neuron, for every weight, some changes, some gradient information. And then I thought, hey, why it's becoming so small? And now I got into it. If you see the problem, then where the problem comes from is easier to figure out. And then I came up with a vanishing gradient. And then it was even easier for me to come up with LSTM, because now I have only to construct something where the gradient is not vanishing. I need something where delta error is propagated back. And if it's smaller than 1, I have a vanishing gradient. If it's larger than 1, it's exploding. How can I construct something, a delta error is propagated back, and it stays exactly at 1? The Jacobian is 1. So activation of the whole system to one time step, and the derivative with the previous time step, it's one. And there's okay. Different activation function, have a saturating thing. I always lose something. Therefore, I need a linear function and I need this weight. And now, from the LSTM, I developed the core system, some memory cell, which has a recurrent connection to itself. And the connection is one. And the activation function is identity. So the derivative of the identity is one. It's fine. And if I propagate it back, I multiply it with one. Now I constructed something that error flows back and it is one. Then the next thing is for LSTM, how do I store something in this thing which keeps the error constant? This were technicalities. But you asked concerning Jürgen, I had to work on the chunker system. Now I deviated. I looked at this vanishing gradient, and then I come up with LSTM and found the solution. And as I handed in and I also wrote with input gates, output gates, I wrote everything down from the LSTM in my diploma thesis. It was called Langzeitgedächtnis, which is a German word. I wrote it in German. And it's like long-term memory. And at this time, Jürgen already went to the States, or was close to went to the States. And he already was aware of this chunker system, but he didn't look very much, or at least I didn't get the feedback into this vanishing gradient in LSTM kind of thing, which was not called LSTM at this time point. And I also handed it in, went to the Allianz, worked there outside of the university. But as Jürgen came back from the States, and I asked Jürgen, can I make a PhD? The first paper I made was flat minimum searches. It was also not LSTM. And then Jürgen said, hey, you had something cool in your diploma thesis. At least he was aware of it. He read it. Should we publish it? Does it make sense? Can we look into it? And now here we have the vanishing gradient and the LSTM. And the LSTM technique we even submitted to NeurIPS in 1995. And got rejected. That was my first thing I wrote in my diploma thesis. And then the first publication was a rejection. And therefore, for all guys who listen to this podcast, be happy if you get a paper rejected. It can turn out very successful for you. Don't be frustrated. That's normal. And in 1996, we really got it at NeurIPS. And in 1997, we had the short publication, Neurocomputation. And later on, there were other guys like Felix Gers, who improved at Jürgen's lab the LSTM method. Added stuff, and then also Alex Graves, also at Jürgen's lab, worked with LSTM and made it, improved it by the CEC, by some specific learning techniques. And then Alex also went to Geoff Hinton. Then these guys got aware of the system, and it became more and more popular. In Jürgen's lab with LSTM, the first guys also won Chinese handwriting competition, stuff like this. And at this time, it became more and more popular. And since 2011, 2012, all big IT companies, Google and Facebook and so on, picked it up and used it for text and language. Nowadays, they're using transformer or BERT models, but at this time, LSTM was the primary method. And these days also, if you look at AlphaStar or OpenAI 5, this reinforcement agents are LSTM networks. Or if you look at Tesla, Andrew Carpenter said he is using LSTMs for for Tesla self-driving component, but it's changing constantly, but it's still in heavy use. For example, also we have the best models in climate change, in hydrology, and these are LSTM models. They're better than the physically constructed models from the experts. LSTM is still very, very popular in many, many disciplines.
This is so interesting, Sepp, that you say that it's in hydrology, you have the best models with LSTMs. And I can imagine that when an engineer comes or someone who has like his formulas and pen and paper, they maybe got a bit annoyed that you come with an LSTM, because in hydrology, I think something like, they call it in German Gletscher, like how it, like ice and water, how it actually transforms and things like that, thinking back in time. LSTMs perform better because they can memorize what actually happened in nature. And now the engineers come more like with pen and paper and they say, hey, well, we couldn't calculate that, but the LSTM can. So this is one of the big advantages of LSTMs. This is so interesting that you mentioned this.
Yeah. But what you're saying, it's exactly what happened for the hydrology, because you have different water storages. It's in the river, of course, but it's also in the soil. And how much the soil stores water depends on the vegetation. And if you have the vegetation as input, you can see, as you said, it's glacier, but it's also snow. Which is melting down, and if the sun is coming, and now water comes down, but you have these different water storages: snow, glacier, soil, but also underground water is one factor. And this their memory cells are building, and we even figured out there was one memory cell. It's exactly how many snow you see outside, this memory cell reflected. And therefore it was a perfect fit for these systems which store things over time. And therefore this LSTM was so good, because you have even physical models, but they're not perfect, because the soil is not perfect, this soil. Or the snow melts a little bit faster or slower, because it depends also if the snow has dirt on top of it. It gets warmer if it's dark, if it's black, and it melts faster. There are small differences and things where a data-driven model can adjust to. It has the same dynamics as you can derive by physics, but it can adjust to the particularities of the thing you're looking at this specific river or this specific region.
This is so interesting. Thanks for sharing the story, Sepp. And I think engineers listening to this podcast will now appreciate what LSTMs can actually do when we talk about data-driven modeling, physics-informed neural networks, things like that. There's a lot of movement going into this direction. Before we move to the application, Sepp, can you explain to the audience in very short terms, like no pun intended, like long short-term memory, and what does it actually stand for? Well, it says long, it's a long short-term memory. What does it actually mean? Just in a few sentences.
Yes, that's funny, because I already touched on it. In my diploma thesis, I only called it long-term memory and Langzeitgedächtnis. And then Jürgen, as we talked about, said, hey, Sepp, in this neural networks, there are two kinds of things which store information. This is the synaptic weights. The synaptic weights are the long-term memory, but you're talking about the activation of the neurons. I would view this, Jürgen said, as a short-term memory. But what you construct is a short-term memory, but which can store a long time, a long short-term memory, and therefore we renamed it. And yeah.
Yeah, I think that clarifies it. Thank you so much. And although LSTM, long short-term memory, seems like a complicated term for a lot of people, we use it every day. Like we have it in our smartphones. Can you explain where we find LSTMs in our smartphones, for example?
Often I don't know where it's used anymore, and sometimes it's replaced by new techniques like transformers and stuff replaced a lot of things. But it was used for in the smartphones for many things. It was for QuickType, for example, in the Apple thing, is completing the word you type in. It was used in Alexa for recognizing the language. It was used to recognize text for sentiment analysis, for example. But also Amazon, for example, used it for translating. And translation was such a big thing because if you in France and put a product or something on the Amazon web, you describe it in French. But in London, perhaps somebody wants to buy it but cannot read it. But if it's translated automatically, it don't have to be perfect. You sell much more. And therefore it has a big impact in this automatic translation thing, because it have to be fast, and you cannot afford all this human guys who translate it. Translation was one of the big applications. Big applications were also what I already mentioned, this reinforcement learning methods. So I used it also in medicine and biotech. So have been used for EEG data analysis, also for DNA and protein analysis. They are often they use the bidirectional LSTMs, where LSTMs scan a sequence from both sides and meet in the middle to make a prediction. All kind of things. And now there's a time where LSTMs more and more are used in physics-informed methods. And that's interesting, because first it was a movement from LSTMs to transformer, which have this huge, big things, because the whole sequence is always presented all the time. But if you now have many, many time steps, let's say you have 1,000 time steps or whatever, you cannot do it anymore with transformers, because they would scale quadratically keys and queries. And now for some of the simulations, they fall back to LSTMs, because LSTMs compress it. They store something in the memory cell, but don't keep the all information all the time. And now more and more this physics-informed methods, it could be from graph neural networks to neural ODEs and stuff, also methods where you solve partial differential equations. This were used to have a very concise representation of your past, where you only store what's needed. Transformers give you everything, but for long sequences, you only want to have very specific pieces of information. And they're coming back right now in these systems.
Is it also the so-called Hopfield networks? I'm not an expert. Like, is this also one part of these other networks that are very, very powerful?
Hopfield networks is nice that you address it. It has nothing to do with LSTMs, first of all. These are associative memories, which are very, very powerful. We introduced this continuous Hopfield networks. The continuous Hopfield networks are differentiable. Therefore, they can be integrated into deep learning. Now, I'm telling you why I'm so fond of this topic. I think deep learning sucks how it is right now. It does not work proper, because it's only you have the input and go to the output, and only have something like a functional approximation. But I think it's not sufficient. What we humans do, if we process some input, we associate it constantly with something else. If I show you a picture of a woman in a white dress, you say, no, that's a wedding dress. You immediately, you see it once and you all see it immediately, that's a wedding dress. Without I'm telling you it's a wedding dress, but you have immediately these associations. And it even helps to remember, we did this, we showed a couple of pictures, and if there was a wedding dress, there was one wedding kind of thing. If you have two wedding kind of things, perhaps the wedding dress plus a church where they exchange rings or whatever, then you remember it, because it's also associated. Then it's association within the sequence. It's episodic memory. Therefore, we do association with a long-term memory, things which are associated. If I show you a fork, you always say, perhaps there's a spoon and a knife missing. You immediately know what's going on. And if I show you a glass, I say, that's a wine glass. You immediately have wine in your mind. But there's also this short-term, this episodic memory, where you memorize, like if we are talking, what I talked a minute before. You're have this episodic memory. And if you get a new input, perhaps here acoustic or whatever, you always associate it. And we don't do it with deep learning. That's a horror. We should associate everything we do, connect with our knowledge, and Hopfield Networks will give you this. You store something in the Hopfield Networks, you get some context, you do processing, but include context. And I think that's one of the future directions I'm convinced they will come. There are many publications. Also, DeepMind is trying to get access to the World Wide Web by associations. You have some words. Look up perhaps Wikipedia pages about this and stuff like this. It's coming. We don't do function approximation. We do always associations with our experience.
Yes.
Also, deep learning have to do it at some point. And we do it with modern Hopfield networks.
So interesting. Maybe you can give us a talk maybe on this channel on Hopfield Networks, and I will put papers from you on Hopfield Networks in the description so everyone can check it out. Very interesting. You mentioned DeepMind, OpenAI, and Amazon. There's a funny story where Amazon used self-normalizing neural networks, or SNNs, and you were on a conference, I think at Long Beach, and they shook your hand and they made the $1 billion profit, if I'm not mistaken, and they bought you a Mojito instead of giving you part, like a chunk of that $1 billion, which brings also problems with it. Maybe you can first explain the story, like how it went with Amazon. Maybe maybe how they used it, but I think they didn't tell it to you. And then what the big problem is, for example, American companies using your technology or Chinese companies using your technology, but Austria or European countries only getting a Mojito. Maybe you can talk about this.
Now the story is following. We did this self-normalizing networks, and I don't remember, probably it was even Europe's at Long Beach, and at some of these parties, some guys came to us, to me and Günther Klambauer is first author, developed this also, and so I said, thank you for inventing this. Thanks a lot. Said, we are here from Amazon. We flew in to shake your hand. It's great what you did, because this was give us $1 billion increase of turnover. And said, we give you a Mojito for this. Actually, it was 2 mojitos because I got one and Günther also got one. That was what I thought. Okay, so Americans make $1 billion, and we Europeans get one Mojito. $1 billion Mojito, $1 billion Mojito. Is it fair? Is it good? I don't know. Afterwards, they wouldn't tell me why it was good for them. Afterwards, I figured out because I think it was, I don't know for what we're using it, either for ads or for translation or something like this, but it was because the self-normalizing networks didn't use batch normalization. So batch normalization costs so much time in the application, if you in inference, that self-normalizing networks were much faster. And for them, the speed was the important thing. To get the ads or to get something faster on the screen, this made them this turnover. I don't know how they calculated it. And here is also a problem. The problem is, the money is not equally distributed. Or it's only turnover. Who knows how much more money they make. But the thing is that the European companies didn't pick it up. I had this LSTM. It was picked up by the East Coast, West Coast Americans, by also at the coast Chinese companies and so on. And the Europeans, even the car companies, we are working with car companies, we are very conservative to picking it up. It was with LSTM, and then I saw it with self-normalizing networks. I also got, in this week, an email from an Apple, the main Apple developer for something. He also saying, thank you for the self-normalizing networks, because now they can implement it in much faster, whatever. And we get thanks. Here, it wasn't even a Mojito we got only an email. And the question is, or what I'm trying to do is, let's do it better. And that was my big thing. Here in Europe, perhaps we are not so strong in this IT business, in this stuff, but where we are strong is in engineering, construction, production things. Why not getting in lead in applying AI in production, in industry, stuff like this, where you really you don't have the internet, you don't have language, but you can apply AI in smart factories, in smart production. And that's what I trying to get these companies, because otherwise also the DeepMinds, Googles, Facebooks, Amazons will come and take it over. Perhaps in Europe we are good in building a good engine, a good motor or whatever, but more and more electronics comes in, more and more sensors go into it. And at some point, controlling this device, this motor, even if it's very well built, might become more important than the device itself. Also, if you have some production machine, you have so many sensors and things. If a driller, everything is equipped with sensors and controlled. And here we shouldn't lose the lead. And therefore, I also started an AI study. And one big focus of the AI study here in Linz is on mechatronics. It's exactly on getting this AI technology into engineering into these companies who are focused on production and building up factories and stuff.
Very interesting. And I think also you have a master studies, like a specific subject or master specialization, I would call it, where people can actually take this course in mechatronics.
Exactly. And therefore was a focus. We have even two. One is more in production, one is more in sensoric. We have two mechatronics tracks in our masters because that's the strengths here in Austria, that's the strengths also in Europe and Germany and so on. And I want to educate guys there to also bring this new technology into these domains, because here we are strong and we should stay strong.
Yes. One problem I see though, Sepp, is a lot of talent from Europe is going to America first and foremost because of the huge salaries companies like Google, for example, pay. Where do you see, or how can you motivate academics, maybe not necessarily stay in academia, but how can we maybe commercialize AI or maybe collaborate with the Americans or maybe the Chinese government?
That's difficult. Also, some collaboration are not good because Baidu once asked me, hey, do you want to do some collaboration? It's years ago with us. And in Beijing, we can give you a whole district. It's only for you. And you can do also a data collection, self-driving, or whatever you like, because it would be government supported and so on. So you can do things you cannot do. But the problem was, but stop, the data is not allowed to leave China. And so I said, okay, no, that's not good. I have to move to China or what? Yeah. And sometimes it has advantages, disadvantages, and also ethical reasons sometimes there. Also with collaborations, we had a collaboration like with this hydrology. Google gave us free money because we did so good work in hydrology. So I said, hey, I want to finance this because that's a good direction, how to apply AI in a good way. For other companies, it was hard to get a contract settled, like with Chinese Huawei. We not even could agree on an NDA. Not even this was possible here because, and for some American companies to restrict. Sometimes it's working, sometimes not working. But what we are trying to do here is to open it up. Like my best example is Amsterdam. Amsterdam does a very, very good thing where companies, there's this Bosch lab, there's a Qualcomm lab, there are all these labs, and Bosch and Qualcomm and many other companies finance PhD students. So they want to have the IT right back, but this idea is not very popular here in Austria or in Germany. So companies like we have collaboration with Audi, BMW, and all kind of companies. as I always want to have something or have their own idea in what directions I want to progress. And some I want always IP rights and stuff like this. That's the wrong way, because this AI field, this deep learning field is so fast that it doesn't make sense to make a patent, because half a year later there's a better idea. You cannot execute it because it's better to have some knowledge. You want to bring some knowledge into your company and not have an IP right. And that's what we are seeing with the other companies in Amsterdam. So do it right. Finance something, get the knowledge, perhaps even get the people who are good educated because they make a PhD in your company. That's more worth than IP rights on things which change constantly. It's not like you develop an engine for 10 years and then you put it in a car and you have time. No, it's much faster, everything. And you have to rethink everything. More important is the knowledge. And therefore I always saying companies, finance guys, they do research in complete different direction, but the technology, how to deal with these neural networks, how to deal with these new methods and techniques, how to prepare the data, what are problems, all this information flows in your company, and you can also use very quickly all these new techniques, you have it available. If you say, we want to do exactly this and this, then you're always behind. You download from GitHub, but somebody made the GitHub. You're behind because the guys who made the GitHub are in front. Now, please, guys, finance something where you can get in front, where you are ahead, because it's quite new research. And in the AI deep learning field, there's a high pace, there's a speed of new developments.
Yeah, very nice statement, and Sepp, I would definitely agree here. With respect to time, I have 3 more questions, and then I think we can wrap it up, Sepp. Beautiful discussion so far. A lot of people are afraid of AGI, artificial general intelligence, whether they watch movies like Ex Machina or Terminator. But do you think this is a valid reason to be afraid of AI? Do you think at some point AGI will come? What's your opinion on that?
First of all, that's sort of a problem with the whole field, because there were these movies, and it's Terminator, there are machines who kill humans, or Matrix, humans were used as batteries, which I think is a stupid idea, because I think there are better technologies for batteries than using humans. And everybody sees these machines, they want to do it. There are 2 reasons. First of all, we are far away from this kind of machines. You see it via GPT-3 and stuff like this. They're good, but they don't understand the world. They don't have a world knowledge. They don't know social laws, physical laws. They only do statistics, because this piece of words or this fragment was very often used in combination. As I do something like pitching stuff together, which is the statistical sound. And for us, it makes sense, but they don't have a deep understanding. We are far away from this. And the other argument is always, if we get some intelligent machines, why would they hunt humans? First of all, they have no internal survival instinct, because we are in evolution. We are only here because we survived. These machines are built like if I have a pencil here, something like this. Why should the pencil say, I want to survive, I want don't go up? It's not, they don't live in evolution. That's missing for them. They don't have an incentive to survive, to get more resources. But let's say even this happens, they're not there, they don't, they're not in evolution, they don't want to survive, they don't have an inherent survival instinct. But let's say there's something like this. Why would they fight for us on this biosphere? Why not go out to the space where much more resources are there, much more energy, most of the sun energy is out there? Or even they can grow into the earth, get here more resources. Why should they compete where there's plants? We need plants, we need it for food. but these machines don't need it. Why should they hunt humans? That's super stupid, because you don't compete for the same resources. Perhaps energy, but energy is much at other environments like in space or in the Earth, there are more resources for that. And why should they compete with us? It doesn't make sense. Therefore, there are many reasons why I'm not scared. First of all, it will not come soon. And I don't think it will come at all, because it's a fantasy. Because we as humans are a little bit arrogant. We are arrogant in saying, hey, everybody want to be like us, and they will compete for us. They want to have the same strawberries or the same things we are eating. Now, perhaps others have complete different interests, and I would say these machines have complete different interests and will not compete with us.
Interesting viewpoint, Sepp. Maybe one could say one of the objective functions for AI could be eliminate all disease. Maybe AI could think that humans are a disease and therefore eliminate all humans. But there are a lot of pro and con arguments. But as you said, and I think your argumentation is very sane and makes a lot of sense. You as an AI expert, Sepp, what would you recommend people to do? What prerequisites do you need to become an AI expert? What would you tell people?
Yes, that's an interesting one. AI experts on different levels. You can entrepreneur or something like this. But let's say what would be good for a PhD kind of thing, where you do profound research. What I always see is to have good programming skills helps a lot. To be good in math helps. And to have a feeling for the hardware, GPUs, storage things helps. And then the fourth thing is communication skills, because often you have an application field, you have to talk to others. It's if you have a super smart idea, but you cannot communicate it, or you want to solve a problem, but you cannot talk to the medical doctors or to the engineers, whatever, it's good. But first I would say programming skills, math skills, hardware skills, communication skills. That in this order I see is very, very helpful. But it's not so fixed because you can team up. I'm a good programmer. I'm a good math guy. Now we put these guys together. One develops a new algorithm, the other programs it, and they both together do a good job. You can do it in teams. But this is what I see in my PhD students who are successful. And that's very complicated, because this broad set of skills, few people have this. It's not many guys who have this broad skills that you're good in programming, but at the same time good in math. And then you can talk to people.
Yeah, I see. Makes a lot of sense. Sepp, any last motivating words out to the world, to our audience, maybe your audience and my audience? Maybe we talked about AGI, how AI can be used in the wrong way, but maybe motivating words, why people should follow the dream of AI, maybe not stay in an AI winter, how to pursue the AI dream, if we can call it like that.
I think it's a big opportunity. There were different industrial revolutions. Some machines came in, and some micro electronic comes in, and sensor computer came in. These were all tools which help to make your life easier. If you look how we are living right now with also computers and machines we have a higher life standard. We live longer than we did a couple of 100 years before. And now we have computers. Now think about each of the computer would intelligent and will help us. That would be a huge advantage for us humans, because things, first of all, humans don't have to do the stupid things, but you make things much more efficient. You can, some very simple ideas for food, producing food. Now you put water, or you put some things across the fields and distribute it equally. But if you have drones, you can see, hey, here's water needed. Here's a parasite, I put something here. You can do it much better than your food. You have less resources used up, and your food is healthy because it's not poisoned by all the stuff you put on the field or whatever. And you can do many things much more efficient, much better. And the life standard and also feeding the whole world, even if it would be a big opportunity for health. Of course, we have health problems, but also look at the third world. Many guys there are poor, but they have a cell phone, but they don't have water. But AI can help also make these countries more efficient in using their resources, and that there's no hunger anymore in these countries, because if they have this technology, it doesn't use a lot of energy. Say AI, and if you have solar current and stuff like this, perhaps this country can benefit a lot from these technologies. I think AI can make a better world.
That's a very nice closing remark from you, Sepp. First of all, thank you so much. It was really an honor to have you on my show. And of course, I will put your Twitter link. Follow Sepp. He recently shares a lot of good papers. Follow Sepp. I'll share also the link to a few interesting talks to you, but also Hopfield Networks. So as you heard from
cool.
Sepp, you have to check that out for sure. And maybe in a second part, Sepp, you can talk a little bit more in depth about Hopfield Networks and the latest research. But this first part, I really appreciate you being on my show. It was an absolute pleasure. I learned so much. And maybe Germany is not so far from Austria. Maybe we can meet not for Mojito, but maybe something else.
That would be great.
Yeah, awesome.
Thanks for having me. I enjoyed it very much. It was a pleasure. And let's do it again.
Yeah, thank you so much, Sepp. Take care.
Okay. Bye-bye. Ciao.